So today we're in section 9.1. Section 9.1 is about correlation. So quite a bit of statistics and statistical investigations are centered around relationships. Sometimes these relationships are cause and effect, and other times they're not. For instance, you may be trying to determine if there's any relationship between the speeds at which you drive and the fuel consumption of your car. You might also be investigating whether there's any relationship between the number of students in an elementary school class and the performance of those students on standardized tests. These investigations would be about correlation. So we need a definition for correlation. A correlation is a relationship between two variables. If we let the variables be x and y, then we can represent them with ordered pairs x, y. The variable x is the independent variable, also called the explanatory variable. The variable y is the dependent variable, also called the response variable. So, because the variables can be expressed as ordered pairs, information from your investigations can be graphed on a coordinate plane. As you look at the data, you can't see patterns unless you have multiple data points. When you graph these multiple data points, you get what's called a scatter plot. Remember we saw scatter plots back in section 2.2. And there are 4 categories for scatter plots. There's actually more than 4, but there's 4 that we're going to focus on here in this particular section. So the first category for a scatter plot is going to be positive correlation. The second category is negative correlation. The third category is no correlation. And the fourth category is a nonlinear correlation. So we're going to see some graphic examples of each of those different types of correlation. So we'll start with positive correlation. With the positive correlation, you're going to see the points on the graph trending upward from left to right. So it looks like you're climbing a hill as you go from left to right in a straight line-ish fashion. So it's not going to be a perfectly straight line, but you get the idea that there is a straight line process going on here. They're all following a path. They're kind of it's like a fuzzy line when you think about it. That's what positive correlation looks like. Negative correlation will have the same type of motion, but instead of going up from left to right, it goes down on the graph from left to right, but still following a straight line path. Even though they're not all on a straight line, they follow a straight line. No correlation would be a graph where the points on the scatter plot are very much scattered around. There may be little clusters here and there, but there's no pattern, no line that they're following, no path through space. They're just scattered about all over the place. And then for nonlinear correlation, there is a path that they're following, but it's not a straight line. So, for example, here we have a nonlinear correlation where the points are following a parabolic path. It doesn't just have to be this shape, though. It could be many different nonlinear paths. They just will follow a curve of some sort instead of a straight line. So let's look at an example. A health fitness researcher wants to know if there is any correlation between the number of hours a person works out per week X and the number of blocks they can run without stopping Y. 20 people are studied, and the results are shown in the table below. So we have this table, and there are 20 entries in this table. So the top number in the X row represents the total number of hours a person works out per week, and the bottom represents how many blocks they can run without stopping. We're talking about city blocks. So the first person works out 7 hours a week, and they can run 9 city blocks without stopping. The second person works out for 5 hours a week and can run 6 city blocks. Another person works out for 4 hours a week and can run 5 blocks. Working out for 9 hours, this person runs for 10 blocks. Then a person who works out only 1 hour a week can only run 3 blocks. A person who doesn't work out at all can run 1 block. A person who works out for 4 hours runs 6 blocks. Then 6 hours with 8 blocks, 7 hours with 8 blocks, 10 hours with 10 blocks, 8 hours with 10 blocks, 5 hours with 7 blocks, 3 hours with 4 blocks, 2 hours with 3 blocks, 0 hours with 2 blocks, 11 hours with 14 blocks, 3 hours with 5 blocks, 1 hour with 2 blocks, 12 hours with 15 blocks, and 10 hours with 12 blocks. So we want to create a scatter plot and see if when we look at the scatter plot, there's any one of these 4 types of correlation present. Is there a positive correlation, negative correlation, no correlation, or nonlinear correlation present? So we need to create our scatter plot. So we'll put up our data and draw our graph. So we need to plot each one of these points on the graph. So the first point is x equals 7 and y equals 9. So we go to 7, 9 on the graph, and we put a point. Then we'll put a point at 5, 6. So that's the point at 5, 6. Then 4, 5. Then 9, 10. Then 1, 3. Then 0, 1. 4, 6. 6, 8. 7, 8. 10, 10. 8, 10. 5, 7. 3, 4. 2, 3. 0, 2. 11, 14. 3, 5. 1, 2. 12, 15. And 10, 12. So you can see that very clearly these don't all fall on one straight line, but there's definitely a straight line path that they seem to be following from the bottom left to the top right. When the straight line path takes you from bottom left to top right, then this kind of a graph would be a graph that represents a positive correlation. So based on the graph, there seems to be a positive correlation between the hours that the person works out per week and the number of blocks they can run. So here's a practice problem for you. A sociologist wants to know if there's any correlation between the number of years a couple has been married, X, and the number of times that they go out to dinner each month, Y. 15 couples are studied, and the results are shown in the table below. So we have 15 data points. We have a couple that's been married 4 years, and they go out 5 times a month, 9 years with 7 times a month, 1 year with 4 times a month, 3 years with 14 times a month, 5 years with 2 times a month, 6 years with 7 times per month, 4 years with 1 time per month, 2 years with 6 times per month, 2 years with 2 times per month, 7 years with 9 times per month, 3 years with 2 times per month, and 8 years with 2 times per month, 2 years with 18 times per month. Wow, they go out a lot. They probably don't know how to cook. 6 years with 12 times per month, and 11 years with 4 times per month. So your instruction here is to create a scatter plot and describe any visible correlation. So give yourself a chance to do that problem, pause the video, and when you're ready to see the answer, press play. Okay, so let's take a look at the solution. We have our data and our graph. So when we graph these points, the scatter plot you get should look like this. This graphs all of those 15 points. And when you look at this graph, do you see any kind of correlation, a positive correlation where all of the points are trending upward along a straight line path from left to right, a negative correlation where all the points are trending downward from left to right along a straight line path, no correlation where the points are just kind of scattered around, or a nonlinear correlation where they're following a path, but it's not a straight line path. It's some kind of curve. So here we see that these points are just kind of scattered around. So this leads us to believe that there doesn't seem to be any correlation. This would be a no correlation situation because they're not following a defined path. They're just kind of scattered all over the place. So based on the graph, there doesn't seem to be any correlation between years married and number of monthly outings. All right. So when you're looking at a graph, you can kind of determine correlation, but it's really an imprecise practice. To get a better idea, we're going to turn to an algebraic method, which is called the correlation coefficient. So the correlation coefficient is a formula that measures the strength of the correlation between two variables. And the formula for the correlation coefficient looks like this. That is a big boy formula right there. That formula is scary to look at. But when you break it down based on what we've learned about the symbols and what they mean, it's really nothing more than some additions and subtractions, multiplications, and division. It's the 4 arithmetic operations that we learned in elementary school. It's just how do we apply them. So R here is our correlation coefficient, and N is the number of data points. So let's read through this formula and figure out exactly what it's saying. So when we see this formula, the N is the number of data points. So we see N in there 3 different times, once in the numerator and twice in the denominator. Then we have sigma of xy in the numerator. Remember, the sigma means add some stuff up. xy means we're going to multiply each x coordinate times its y coordinate. So this says multiply the x's times the y's, each x times its own y, and then add up all those products. Then the second part of the numerator says we've got 2 sums. We've got the sum of all the x coordinates and the sum of all the y coordinates, and we multiply those together. So you add up all your x's, you add up all your y's, and you multiply those 2 numbers together. Then you're going to subtract the n times the sum of the xy's and the sum of the x's times the sum of the y's. In the denominator, there's 2 square roots. You have to take each x and square it and add them up. You have to take the x's and add them up and then square them. Same thing with the y's. You have to square them and add them, and then add them, then square them. And this value will be your correlation coefficient. So what are the properties of the correlation coefficient? Well, the value will always be somewhere between -1 and +1. If you compute a correlation coefficient and you get some value that's not between -1 and +1 on your calculator, then you did it incorrectly, and you need to go back and figure out what went wrong. If you have a perfect negative correlation, it will have a value of -1. What a perfect correlation is when you graph your scatter plot, there's no scattering at all. They're all on a straight line. So a perfect negative correlation would mean that all the points are on a perfectly straight line, not a fuzzy straight line, a perfectly straight line from top left to bottom right. A perfect positive correlation has a value of +1 for its correlation coefficient. So again, perfect correlation means they fall on a straight line, not a fuzzy line, a straight line. And this would be a positive correlation, so it would be a straight line going from the bottom left to the top right. The stronger the negative correlation, the closer R will be to -1. So as the line gets more and more defined, when you look at your points, as it gets closer and closer to being a perfectly straight line, then those correlation coefficients will get closer and closer and closer to -1. The stronger the positive correlation, the closer R will be to +1. So as that value of R increases towards +1, the points are closer and closer and closer to being on a perfectly straight line. And lastly, when there's no correlation between x and y, then the R value will be close to 0. Let's look at an example. So find the correlation coefficient for the data in the previous practice problem. So you just finished doing a practice problem about how long couples had been married and how many times they go out per month to dinner. We're going to go ahead and take that same data and find the correlation coefficient. We pretty much already know what the answer should be. Not exactly, but what we're expecting is a value that's close to 0. Because when we looked at the graph of that situation, we saw that there was no straight line path or curve path that they're following, and that they are scattered about. So here's that data again, those 15 values representing the X, which is the number of years that they've been married, and the Y, which is the number of times they eat out per month. So here's our solution. We need to expand our table because in the formula for the correlation coefficient R, we needed to find values for X times Y, for X squared, and for Y squared. So we're going to have to compute each one of those values. So what I've done here is I have my table with the original data. The first row is my X's of 4, 9, 1, 3, 5, 6, 4, 2, 2, 7, 3, 8, and 2, 6, 11. And my Y's, which are 5, 7, 4, 14, 2, 7, 1, 6, 2, 9, 2, 2, 18, 12, and 4. I've added in a row for X times Y, a row for X squared, and a row for Y squared. And then at the end, we've added in a column that represents the sum of the rows. So let's go ahead and fill out this table. We'll take our time and do it right. So the first new row represents X times Y. So in the first column, my X is 4, my Y is 5, so 4 times 5 is 20. Then I have an X of 9, a Y of 7. Multiply those together, we get 63. 1 times 4 is 4. 3 times 14 is 42. 5 times 2 is 10. 6 times 7 is 42. 4 times 1 is 4. 2 times 6 is 12. 2 times 2 is 4. 7 times 9 is 63. 3 times 2 is 6. 8 times 2 is 16. 2 times 18 is 36. 6 times 12 is 72. And 11 times 4 is 44. So that completes our row for X times Y. The following row is for X squared. So we're going to look at each X coordinate and square it. That means multiply it to itself. So 4 squared, 4 times 4 is 16. 9 squared, 9 times 9 is 81. 1 squared is 1. 3 squared is 9. 5 squared is 25. 6 squared is 36. 4 squared is 16. 2 squared is 4. 2 squared is 4 again. Then we have 7 squared, which gives us 49. 3 squared gives us 9. 8 squared gives us 64. 2 squared gives us 4. 6 squared gives us 36. And 11 squared gives us 121. So that finishes our row for X squared. Now we have to square our Y values. So 5 squared is 25. 7 squared is 49. 4 squared is 16. 14 squared is 196. 2 squared is 4. 7 squared is 49. 1 squared is 1. 6 squared is 36. 2 squared is 4. 9 squared is 81. 2 squared is 4. 2 squared again is 4. 18 squared is 324. 12 squared is 144. And 4 squared is 16. So now that we have all of these rows complete, we can add up each row because that's what we need for the formula. We need the sum of the X row, we need the sum of the Y row, the sum of the X times Y row, the sum of the x squared row and the sum of the row for y squared. So we'll start with the x's. 4 plus 9 is 13, plus 1 is 14, plus 3 is 17, plus 5 is 22, plus 6 is 28, plus 4 is 32, plus 2 is 34, plus 2 is 36, plus 2 is 43, plus 3 is 46, plus 8 is 54, plus 2 is 56, plus 6 is 62, plus 11 is 73. Then we'll add the next row. 5 plus 7 plus 4 plus 14 plus 2 plus 7 plus 1 plus 6 plus 2 plus 9 plus 2 plus 2 plus 18 plus 12 plus 4 is 95. For the row representing x times y, 20 plus 63 plus 4 plus 42 plus 10 plus 42 plus 4 plus 12 plus 4 plus 63 plus 6 plus 16 plus 36 plus 72 plus 44 ends up being 438. When we add up the x squareds, 16 plus 81 plus 1 plus 9 plus 25 plus 36 plus 16 plus 4 plus 4 plus 49 plus 9 plus 64 plus 4 plus 36 plus 121 equals 475. And the last row for the y squareds is 25 plus 49 plus 16 plus 196 plus 4 plus 49 plus 1 plus 36 plus 4 plus 81 plus 4 plus 4 plus 324 plus 144 plus 16, which adds up to 953. So we now have these 5 sum values. We're going to use those to fill out our formula for the correlation coefficient. So our formula says we have n times the sum of x times y minus the quantity of the sum of x and the quantity of the sum of y multiplied together, divided by 2 square roots. The first square root has n times the sum of the x squareds minus the sum of the x quantity squared, and the second square root has n times the sum of the y squareds minus the sum of the y's quantity squared. So we're going to insert what we know. The n, remember, is how many data points we had, and in that situation we had 15. So we have 15 times the sum of the x times y. Well, the sum of the x times y's was 438, minus the sum of the x's, which was 73, and the sum of the y's, which was 95. Then in the denominator, we have 2 square roots. The first square root has the n times the sum of x squareds, so that's the 15 times 475, minus, it says take the sum of the x's and square it. So the sum of the x's was 73, so we have 73 squared. The second square root contains n times the sum of y squared, so that's 15 times the 953, then minus the sum of y quantity squared. Well, the sum of the y's was 95, so we have 95 squared. When people see a problem like this, they try to enter it into their calculator all at once because they want the calculator to do the math, because it looks like there's a lot of difficult math there. Instead of approaching it that way, you should continue to simplify. You can use your calculator to do it, but continue to simplify the numbers down so that when you try to enter it to get a final calculation, you're not entering complex computations like multiplications and subtractions and square roots that contain operations. You would like for there to just be one number on top and 2 simple square roots on the bottom. So that's what we're going to do here. We're going to go ahead and do our multiplications. There's 6 multiplications to do. We have to do 15 times 438, which gives us 6570, and 73 times 95, which is 6935. That's our numerator, and we're subtracting those 2 values. In the denominator, we have 4 multiplications to do. 15 times 475 is 7125, and 73 squared, which means 73 times 73, is 5329. The next square root has 15 times 953, which is 14,295. And then you're subtracting 95 squared, and 95 times 95 is 9,025. So it already looks a little bit simpler than it did in the step above, but we can simplify more. There are now 3 subtractions to do. So we'll do 6570 minus 6935, which is negative 365. And then in our square roots, we'll have 7125 minus 5329, which is the square root of 1796. And then 14295 minus 9025, which is the square root of 5270. So this is much easier to enter into your calculator than it would have been when we had just entered the numbers. Now a good exercise is for you to try to enter this into your calculator to see what you get. There are very common mistakes that students make when they're using their calculators because the calculator will follow the order of operations better than we do. We know what we mean when we put something in, but if it's not quite entered correctly, the calculator interprets the formal order of operations, not what we mean. So try to enter that into your calculator to see what you get, and we'll see what it is in just a moment. When you enter that all into your calculator, you should get negative 0.1186408886. Now if you didn't and you got a much larger number, then the mistake you made is probably a mistake in the denominator. So when you're entering this into your calculator, you enter the numerator, negative 365, you hit the divided by key, and then the denominator in its entirety has to be in a set of parentheses. So oftentimes students will just enter negative 365, then hit the divided by key. They'll put in the square root of 1796, and then they'll hit times the square root of 5270. The order of operations does not interpret that the way that we have it written here on the screen. What you need to do is put your entire denominator in parentheses. So you would put negative 365 divided by parentheses. Then you put the square root of 1796 times the square root of 5270, and then end your parentheses. That makes sure that the two numbers that are being multiplied together in the denominator are grouped together, and that means the calculator reads that as one number for your denominator. Otherwise, if you don't put the parentheses, then it will divide the negative 365 by the square root of 1796, and then take that fraction and multiply it by the square root of 5270, which is not what you intend to do. So use your parentheses to group your entire denominator together, and that should solve your problem. So this is our correlation coefficient. And based on this correlation coefficient, that goes to justify what we said when we looked at the graph. Remember, when we looked at the graph, we said there's not really any correlation here. And they're just kind of scattered all about the graph. And this value, negative 0.1186408886, is pretty close to 0. It's not close to negative 1 or positive 1. It's hovering right below 0. So that tells us that there's not really any correlation here. Okay. So this process is kind of long. The individual pieces aren't particularly difficult as far as the math that we have to do. We have to multiply some numbers, we have to add some numbers, we have to subtract, we have to divide. We're basically just using the 4 operations, and then we'll throw in a couple square roots. But even so, when you put them together in such a complicated formula, it can make this process very difficult. But the TI-8384 graphing calculator has the capacity to compute the correlation coefficient. Before we do that, there's something we need to do to set it up. So what we're going to do, when you turn on your calculator, you're on your home screen, and you're going to hit the second function button, and then the 0 button. And the reason that you hit the 0 button is because there's a secondary menu above the 0 button that says Catalog. And we need to get to the catalog of functions. So when you first hit Catalog, it looks something like this. where it has several different functions laid out below the word catalog. And you're going to scroll down until you see the function diagnostic on. When you get there, you press enter. That will put diagnostic on your home screen. Then you press enter again, and it will say done. I've got a little asterisk here. You only have to do this once. Once you've turned the diagnostic on, it stays on for as long as you own the calculator, or I guess until you change the batteries. So you don't have to keep turning it on every time you do the problem. Once you've done a correlation coefficient problem once and turned the diagnostic on, it stays on. So this is just a one-time thing. The rest of the problem you might do different times depending on the problems that you're doing. But to turn the diagnostic on, you only have to do it once. Then what you're going to do is you're going to press the Stat button, and you'll see this screen. And we want to hit enter immediately, because that's going to take us to the list edit screen. Now, if you have numbers in your lists already, for instance, if you borrowed your calculator from the library and there's data in that from the last student, then what you can do is to empty out the data. You go up and you highlight the name of the list, L1. You press the clear button on your calculator, and then you go back down into the list, and it will clear out all the data. Once you have your empty list, what you're going to do is you're going to enter all of the x coordinates in L1 and the y coordinates in L2. You want to make sure you keep those coordinates in the same order. Don't go changing the order around. The reason you want to keep them in the same order is because one of the values that we compute is x times y. So when you're doing that, you have to multiply each x times its own y. So if you change the order, you'll be multiplying the wrong x's and y's together, and that will change that sum. Once you have your data values entered, then you're ready to compute the correlation coefficient. So you press second and then the mode button, and that takes you back to your home screen. Then you press the stat button, and it takes you to our stat menu. We're going to use our arrow keys to move that top highlighted tab from Edit over to Calc. So you move the cursor so that Calc is highlighted, and then you're going to find the command linereg ax plus b. That's linear regression in the form ax plus b. Then you press enter, and it puts that at the top of your screen. And then if you press enter again, then you'll see all this information. So we've got a equals negative 0.2032293987, b equals 7.3223833073, r squared equals 0.0140756604, and r is negative 0.1186408886. All those other values, a, b, and r squared, we don't need yet. Those are coming down the road a little bit. But the very bottom value is the r. That's the correlation coefficient that we just found when we were doing the problem about the people going out to dinner and how long they had been married. Had you not turned the diagnostic on, then you would only see the a and b value. You wouldn't see the r squared and the r. So that's why we had to do that diagnostic on command, because otherwise it wouldn't give us the correlation coefficient. But since we turned the diagnostic on, we got that correlation coefficient, and it did all the calculations for us. So that's a very nice process there that shortens the amount of work we have to do. So again, that r at the bottom is your correlation coefficient. Alrighty. So once you can compute the sample correlation coefficient, you need to determine if the population correlation coefficient is significant. So in other words, does having the amount of data we have and getting the correlation coefficient that we got give us enough information to say something about the population correlation coefficient? And so we want to know whether we can use a few data points to make inferences about the entire population. When we make a decision like this, it's always possible that we mess it up, that we make an error. So the percentage of times we believe a correlation is significant, when it actually is not, is called the level of significance alpha. We usually set alpha at 0.05 or at 0.01. Those are the standard values for alpha, although you could set it at 0.03 or 0.02, but the standard values are 0.05 and 0.01. So, how do we determine if the correlation coefficient is significant? Well, first we calculate our number of data pairs, decide on your level of significance alpha, find the critical value from a table, and the table is called the table of Pearson correlation coefficients. Find the value of R, and then compare the critical value to the absolute value of R. If the absolute value of R is greater than the critical value, then the correlation is a significant one. So, how do we find those critical values? Well, we have this table. And so if we have an n value, remember n is our number of data points, we can find that, and then this gives us values for the 0.05 and 0.01 levels of significance. So for instance, if we had 10 data points and we were at the 0.05 level of significance, then the correlation coefficient would be 0.632. And that's what we would compare the absolute value of R to make our decision about whether or not the correlation was significant. So here's an example. The following data represents the number of students in 8 fifth grade classes X and the average number of discipline problems per week Y. Find the correlation coefficient for the data and determine if there is a significant correlation at the alpha equals 0.01 level of significance. So here's our data. We have the number of students in the top row for our X's, so 24 students, 29 students, 26 students, 23 students, 30 students, 25 students, 26, and 25. And in the row for the Y's, those are how many discipline problems we had per week. So 3 discipline problems, 7, 4, 1, 6, 4, 5, and 5. So when there were 24 students, there were 3 problems. 29 students had 7. 26 students had 4 problems. 23 students had 1 problem. 30 students, there were 6 problems. 25 students had 4 problems. 26 students had 5 problems. And 25 students had 5 problems. So what we want to do is find the correlation coefficient and then determine if that correlation is significant at the 0.01 level of significance. So first things first, we need to find the correlation coefficient, and to do that, we're going to expand our table. So let's look at the solution to this problem. We'll make an expanded table that includes a new row for x times y, a row for x squared, and a row for y squared. So we'll take our x's and multiply them to the y's. So when we multiply 24 times 3, we get 72. 29 times 7 is 203. 26 times 4 is 104. 23 times 1 is 23. 30 times 6 is 180. 25 times 4 is 100. 26 times 5 is 130. And 25 times 5 is 125. For our x squareds, 24 squared is 576. 29 squared is 841. 26 squared is 676. 23 squared is 529. 30 squared is 900. 25 squared is 625. 26 squared is 676. And 25 squared is 625. We'll also square our y's. So 3 squared is 9, 7 squared is 49, 4 squared is 16, 1 squared is 1, 6 squared is 36, 4 squared is 16, 5 squared is 25, and 5 squared is 25. Then we need to get the sum of the x's, the sum of the y's, the sum of the x times y's, the sum of the x squareds, and the sum of the y squareds. When we add up all of our x's, 24, 29, 26, 23, 30, 25, 26, and 25, those all add up to 208. When we add up our y's, 3, 7, 4, 1, 6, 4, 5, and 5, those add up to 35. Adding up the x times y's, 72, 203, 104, 23, 180, 100, 130, and 125 all add up to 937. When we add up our x squareds, 576, 841, 676, 529, 900, 625, 676, and 625, we get 5448. And then for our y squareds, we add those up. We get 9 and 49 and 16 and 1 and 36 and 16, 25 and 25 all added together gives us 174. So now we have the row sums that we need. We have the sum of our x's, the sum of our y's, the sum of our x times y's, the sum of the x squareds, and the sum of the y squareds. We use our formula for the correlation coefficient. So we'll insert the values. This time our n is 8 because we have 8 data points. So we get 8 times the sum of x times y. The sum of the x's times y's were 937. So it's 8 times 937. Then we're supposed to multiply the sum of the x's times the sum of the y's. Well, the sum of the x's was 208, and the sum of the y's was 35. In the denominator, we have two square roots. The first square root says we take the n, which is the number of data points, times the sum of the x squareds, which was 5448. So we get 8 times 5448. And then we're supposed to take the sum of the x's and square that number. So the sum of the x's was 208, so we have 208 squared. That ends our first square root. In the second square root, we're supposed to take the number of data points n and multiply it to the sum of the y squareds, which was 174, so we get 8 times 174. Then it says subtract the sum of the y's squared. So the sum of the y's was 35, so we're subtracting 35 squared. Don't try to enter this into your calculator all at once. Try to simplify each piece before we try to enter it into the calculator. So we get 8 times 937 is 7496. 208 times 35 is 7280. 8 times 5448 is 43,584. 208 squared is 43,264. 8 times 174 is 1392, and 35 squared is 1225. Do those three subtractions. So we get 216 over the square root of 320 times the square root of 167. If we enter this into our calculator, we get a correlation coefficient of 0.9343735293. Now that looks like a very strong positive correlation, right? Because that value, 0.93, is pretty close to 1. But we need to do our comparison to see how significant that correlation is. So what we're going to do now is we're going to go to the table of values, and we're going to compare the absolute value of r to the value from the table. So here's part of that table, the part that we need. We look for where the n value is 8, and we find that row, and then our level of significance alpha was 0.01. So the critical value for us here is 0.834. So we have our absolute value of r, which is the 0.9343735293, and we're going to compare it to this critical value from the table, which is 0.834. Which one of those two is bigger? And the answer is the absolute value of r is bigger. So whenever the absolute value of r is greater than the critical value, then that means the correlation is significant. So here we had a significant correlation. So that's how we determine if a correlation is significant or not. The last thing we want to talk about is this note here. It's very easy to confuse the concept of correlation with the concept of causation. People mess that up all the time. Correlation means that two values have some linked relationship with them, whereas one of them increases, the other increases, or as one of them increases, the other one decreases. That's not the same as causation. Causation means that the action of one of the variables is causing the effect on the other. Just because two variables are correlated doesn't mean that there's a causal relationship there. So we need to kind of flesh out those concepts a little bit. Correlation and causation. So just because two variables have a strong correlation, that does not necessarily mean that the behavior of the variable x causes the behavior of the variable y? There's actually several different things that could happen. So we're going to consider 4 possibilities here. The first, does x cause y? Does the behavior of our first variable, our x variable, cause the action of our second variable y? It could be the other way around. Does y cause x? Is it that the second variable y is what's causing x to do what it's doing? It could be something totally different. What if there's a third unseen variable that's causing the behavior of both x and y to occur? So something that we're not even investigating that's causing both x and y. And then the last possibility, which I think too many people discount, is what if it's all just a coincidence? Just because 2 variables are correlated with one another doesn't mean that they have any causation relationship at all. It could just be that one is going up and the other one's going up at the same time and they're not related at all. There is the opportunity for a coincidence, and it happens a lot more often than people like to admit. People see a correlation and they want to immediately believe there's causation, but that's not always true. So we'll look at some examples of each one of those possibilities. Before we do, we have a little note here. When a third unstudied variable is causing the behavior of x and y, it's called a lurking variable. So whenever there's some unforeseen actor in the background that's causing the results for both the variable x and y, it's called a lurking variable. All right, so let's look at these 4 different possibilities and look at them in context of some situations. Does x cause y? Well, let's say we have this situation. There's a strong positive correlation between the amount of rainfall in Madeira, x, and the number of blue vinyl tarps sold at the Madeira Home Depot, y. In this situation, there's definitely a cause and effect relationship. It's clear that the number of tarps sold doesn't increase how much rain falls, right? So just because they sell a bunch of tarps at the Home Depot, that doesn't mean the skies suddenly open up and drop down torrential rain upon us. It doesn't work that way. But when it does start to rain, people will go out and buy tarps. Maybe they have a leaky roof and they need to cover that, or they have things in their yard that they need covered. So they will buy tarps in response to the rain. So the purchasing of tarps increases when rainfall starts. So that's a causal relationship because the rain is causing people to go out and buy tarps. So in that case, x causes y. What about when y causes x? Well, there's a strong positive correlation between the amount of highway fatalities x and the number of drivers on the highway y. So positive correlation means as one's going up, the other one's also going up. So as there's more fatalities on the road, there are also more drivers on the road. So do you think that having a higher number of fatalities causes more people to go drive? And the answer is no, that doesn't make sense. If I knew there was a lot of fatalities on the road, that might make me not want to drive. So it's not the number of fatalities that's causing more people to drive. It's the fact that more people are driving that's causing more fatalities because the roads have more people and there's more opportunities for people to make errors that can result in life-threatening situations. So is it the case that the increased number of fatalities causes more drivers to be on the highway? Probably not. However, the increase in drivers does cause the increase in fatalities. More drivers, more accidents. Therefore, y causes x. So here we have a causal relationship, but it goes the other way. Instead of x causing y is causing x. How about this situation? Does a third variable cause x and y? So there's a strong positive correlation between the amount of electricity used in Madeira x and the amount of ice cream consumed in Madeira y. So strong positive correlation means as one goes up, the other one goes up too. So as people use more and more electricity in Madeira, then the amount of ice cream that's sold in Madeira goes up. Do you think that higher electricity use causes people to eat more ice cream? Probably not. Do you think that when people eat more ice cream, they use more electricity? No. What's really happening here? Well, this is that lurking variable. This is that third variable that's in the background that's causing both of these things to happen. What is that third variable? Well, it turns out that a third variable, daily high temperature, is causing X and Y. So if you think about it, if it's hot outside, what happens? Well, people turn on their air conditioners. If you turn on the air conditioner in your home, then your electricity usage goes up. And when it's hot outside, people want to go get ice cream because ice cream is a cool treat on a hot day. So it's the third variable, the temperature, that's causing both the increase in electricity use and the increase in ice cream consumption. So there's a third variable that's causing both of these other two things to happen. The last example is the correlation just a coincidence. So there's a strong negative correlation between the population size of Asian carp in Lake Michigan, X, and the population size of the San Joaquin kit fox in the Central Valley, Y. So Asian carp is an invasive species in Lake Michigan. It's believed that those carp got there in the ballast tanks of cargo ships that entered into the lake, and when they emptied out their ballast tanks, these Asian carp swam out and then found themselves a home in Lake Michigan. The problem with that is they're not native to Lake Michigan, and they have no natural predators in Lake Michigan, so they have gone in and basically messed up the ecosystem. They're an apex predator. These carp fish are apex predators in the Great Lakes, and they're not supposed to be there, so they've disrupted the whole ecosystem. Their populations are soaring, and there's nothing there to stop them from getting bigger and bigger and bigger populations. The San Joaquin kit fox, on the other hand, is an endangered species, and it's harder and harder to find them. I saw one near the Madera Center probably a few years ago now, and they're little bouncy foxes. They're smaller than most dogs. They're a little bit bigger than a Chihuahua, but they are smaller than most dogs, and when they run, they bounce. It's fun to watch. I hadn't seen one in years, and then I finally saw one a couple years ago, and I haven't seen one since. So they're not all over the place anymore. They used to be, but not anymore. So their population size is dwindling. So, do you think that the Asian carp's increase in population is causing the San Joaquin kit fox population to go down? The answer is no. There's no relation. There's no geographic connection between the two. They're thousands of miles apart from one another. Do you think that because the San Joaquin kit fox is dying out, that means the carp are growing? No, it doesn't make any sense. They're just not related. But there is a strong correlation there. It's just not caused by anything. It's a total coincidence, right? It's a coincidence that there's a negative correlation here. It's not a causal relationship. There's not some outside force that's causing both of those things to happen, and there's not, a causal relationship between the two where one is causing the other. This is just a coincidental correlation. So that brings us to an end of section 9.1. Please look on Pearson for your homework, and have a great day.